In the previous lecture, we have discussed that how we can use a polytropic process to calculate the work, and we looked at some formulas that can be used to quantify the work. Here let us do an example and let us examine the relation of PV, pressure and volume, because as we have known that the polytropic process is P V की power n is equal to constant. To find the value of n, we first know the relation of pressure variation with respect to volume variation. So if we know that the relation, only then we can use the formulas and we can use it to quantify the work. And we have already seen that the work, due to expanding boundaries, is path dependent. What path the system takes defines the amount of work that is being done on the system or being done by the system. So it is a path dependent phenomena. Work is a path dependent quantity. In this example, we have a piston cylinder assembly in which we have installed a spring over the piston. Now, the statement is considered as slightly different piston cylinder assembly arrangement that we were used to consider in previous lectures and lectures that were delivered during on-campus time. Here there was no spring on it, but we are considering this example to complicate things and then observe the relation of pressure with respect to volume. In this example, the piston is loaded with mass m. Mp is the mass of the piston, and P naught is the external pressure. The spring is linear. The force it generates depends upon the linear compressed length, and then it applies the force F1. The spring applies the force F1 on the piston, and the piston traps the gas inside it, and the pressure inside is P. Now if we draw free body diagram for this piston, this is, this is the piston, and the forces it is countering is F1 force downward, its weight downward, and the force because of external pressure P into A, area of the piston, P naught, the P naught, and then the force that is coming from the gas inside cylinder, and we say it P into A. So these are four forces that this piston is countering. Now if we apply second law of Newton, then and we considered that the system while motion remains in quasi equilibrium state. What is quasi equilibrium we have already discussed on campus classes. So the motion is not abrupt, and we can consider that while motion the motion is very steady, and at an instant we can consider the piston on stationary or something near to zero velocity. So sum of all the forces in y direction is equal to 0, and if we consider the force that which this springs put on piston is ks into x minus x naught. What is x minus x naught? Is the uncompressed length. Length is current length minus its uncompressed length. X is the current length and x naught is the uncompressed length. When the piston, what is the initial length of the spring? You have noticed that springs do not apply force when they are uncompressed, or so if we have a spring whose initial length was 1 meter and we compress it 2.8 meter, so the force will depend upon 1 meter minus 0.8 meter, 0.2 meter difference. The 0.2 meter, x minus x naught will be 0.2. It was just an example. So here's the spring coefficient, and these are the forces. If we put it in the and balance the forces, it will generate this equation. And if we take the force because of gas trap in it to the other side, we will get this equation. And if you notice that external pressure P0 is constant, it's not changing, then the mass of piston MP is constant, it's not changing, gravitational pull is not changing, G is constant, and the spring constant is not changing, it's constant. So area of the piston is not changing, it's constant. So everything in this slide, in this every force, every parameter is constant except the pressure inside the cylinder, and the volume. If we divide the whole equation with the area, and we convert this spring force into the volume, into the these lengths, uncompressed lengths and compressed lengths into the volume. We manipulated this and divided by area, and then we converted these lengths into volumes. So everything is constant, so we denoted it with C1 and C2, two constants, and there is only two variables: the volume of the cylinder that varies, and the piston pressure inside the piston cylinder assembly. So we can see that now piston inside the cylinder pressure is linearly related with the volume. Okay, C1 and C2 are constants. So now we can see that what if we draw it, we will get this line from 1 to 2, and if we wanna calculate the work, in it, we will definitely integrate it and calculate this area under the curve. This area will be our work. If the piston pressure changes from P1 to P2 and certainly V1 to V2, the amount of work being done on the system during this process or by the piston on the surrounding is the area under this curve. So this is another example that we can how we can manipulate things and calculate the work. Another example is, let us consider this piston cylinder assembly in which certain mass is placed on the piston. The cylinder is fitted with a piston on which a number of small weights are placed. The initially pressure is 240 kilopascal and the initial volume was 0.04 meter cube. Now consider we have placed a burner bin under the cylinder and let the volume of gas increase from 0.04 meter cube to 0.1 meter cube while the pressure remains constant. As we already see, we can understand, we can observe that this piston cylinder assembly is a constant piston cylinder assembly in which the gas inside will experience a constant pressure because there is no variable force outside. The pressure P naught, ambient pressure P naught is constant, these weights are constant, so the gas pressure inside will remain constant. So if that's the case and we know PV to power n is equal to constant, now what will be the value of this n so that P comes out constant from this equation? Definitely we will have to put n is equal to 0. For n is equal to 0, we have the formula, that is P2 minus P1 into V2 minus V1 divided by 1 minus n. So n is equal to 0, so it comes out P2 minus P1 into V2 minus V1. And since the P2 is same as P1, so it will take this form, this one. It will take this form, P into V2 minus V1. And we already know that the value of pressure is given, volumes are given, we can calculate the value. Now the second part is where we consider a scenario in which the burner is placed under this piston cylinder assembly. However, during the rising motion of piston, we remove these weights in such a way that the temperature inside remains constant. And when temperature is constant, here we have to put in some certain assumption that we are talking about natural gases, and we can use natural gas law to equate the pressure, volume and temperature relationship, and at state 1 and state 2, and we come out so that in a form that let me write over here that we have P1 V1 is equal to mRT1 and P2 V2 is equal to mRT2. When T1 is equal to T2, we can take T1 out of equation 1 and put it in T2, and we will know that P1 V1 is equal to P2 V2 in this equation. So that means that PV is equal to C. Here n gets the value of 1. So we can use the formula we have discussed in previous slides. When we get the value of n is equal to 1, we have the formula P1 V1 ln V2 over V1. So we can use this formula to calculate the. Another example is that now the value of n is equal to 1.3. So it is already given. Why 1.3 in certain ideal gas scenario? If the process is reversible as entropic process, then the N is the ratio of specific heat at constant pressure divided by specific heat at constant volume. We will discuss these two heats in coming slides. If the process is reversible isentropic process, then we will get this value of 1.3, nearly 1.3 for the air. But we will discuss it in next coming slides and further discuss in thermodynamics too. We can calculate work now because we already know that N is equal to 1.3, and we can use the formula that is P2 minus P1 into V2 minus V1, or P2 V2 minus P1 V1 divided by 1 minus N. So N is equal to 1.3. Now fourth scenario is when if we consider the system with the initial states, and we put a pin in the piston so that piston cannot move now. If piston cannot move, you can definitely guess what the work will be. There will be no change in volume. So when there is no change in volume, there is no work. So for the D part of this example, there is straight away, since the piston cannot move now, so the change in volume is 0. So the work is equal to 0. There will be no work when there is no compression or expansion in gases. There will be no work. So straight away, if we come across any scenario where we do not allow the system boundaries to expand or contract, then we cannot do work on it. We cannot get work from the system. So either way, there will be no work done on the system. We cannot do it, and system cannot produce work and cannot influence scenario in a mechanical way. So there will be no work.